The thing that truly makes the rapid spanning tree rapid is its convergence process. In other words, how does the rapid spanning tree calculate the resulting tree-like structure in a fast and efficient way, and what makes it faster than the traditional spanning tree? The rapid spanning tree convergence consists of synchronization process, which in turn consists of an exchange of messages that we call proposals and agreements. A very common misconception that students have when they are learning about the rapid spanning tree is that the rapid spanning tree is faster or more rapid than the traditional spanning tree because of faster timers. This is not the case, as the timers in use by the rapid spanning tree are pretty much the same timers that are used by traditional spanning tree. What truly makes rapid spanning tree rapid are these proposals and agreements. So let's see how they work. The process of rapid PVST convergence is done using this exchange of proposals and agreements. This process is technically consisting of two steps. One is the handshake, the agreement and proposal and agreement exchange between two switches, and the other one is the process of synchronization. The process of synchronization is what the switch does before it agrees to anything that other switch may have proposed. But I keep mentioning these proposals and agreements without actually talking about them in greater detail. Bear with me. The first thing that I want to mention here before I go on is that this process works only on point-to-point ports by default. Those ports that are not point-to-point, that are shared ports, may need to be configured manually to be point-to-point ports, and remember, this is going to be the case on all ports that are not full duplex, and they can be manually configured to be point-to-point ports. The reason why this works only on point-to-point ports is that this whole idea of handshake, of the exchange of these proposal and agreement messages, is supposed to be happening between only two devices. If we have more than two devices involved on the same network segment, we cannot use this process. And if we have half duplex connection, that may imply that we have a hub, and if we have a hub, that means that we have multiple devices connected to that network segment, and of course we cannot use this process. So this is the first safeguard that is put in place. The next thing that happens is, if this has been satisfied, so if we have this condition in place, is that the handshake happens. And it's a relatively simple process. The switches send BPDUs and they propose that this port that has actually transmitted the BPDU becomes a designated port. The other switch may actually send a superior BPDU, a better BPDU, or it can agree to the proposal. Now, let's say that the other switch does agree to the proposal. Before it blindly sends out the agreement and says, yeah, this is okay, you be the designated port, what it needs to do is it needs to synchronize itself with the topology. Because remember, we may be dealing with more than just two devices. If we are dealing with more than just two devices, blindly changing the mode of operation on the port, transiting from down to forwarding or from discarding to forwarding, could be dangerous. It could lead to bridging loops, and we want to avoid the bridging loops. So before the switch can send the agreement message, it actually needs to synchronize itself with the topology. What does that mean? What this means, of course, is that the switch needs to go through the process. Now, this process obviously consists of several steps. The first thing that happens is that all non-edge ports are moved into the discarding state. The second thing that happens, on the port on which we have received the proposal to which we are just agreeing to, we are actually going to send out the agreement. So we're going to say, yeah, okay, you are going to be the designated port on this segment, and I'm now synchronizing myself. So all the non-edge ports are, at this moment, discarding the traffic. Now, the next thing that we are going to do is we are going to determine which one of our ports is going to become the root port. The root port, remember, is the port that is closest to the root, that has the lowest cost to reach the root. This port is immediately moved to forwarding because we don't want to actually cut ourselves off from the network for too long period of a time. Now, on each non-edge port that is currently in discarding state as the result of this process of synchronization, we are going to send our own proposals. So basically, imagine what happened here. The switch sent out the proposal, this switch here is now agreeing to this proposal and is sending its own proposals out. Let me show you this on the whiteboard. So what we have here is we had the first switch and our second switch here. So this was the link on which we initially received the proposal message. Now we are agreeing on this port here, but imagine that we had other ports here that other switches may have been connected to. So on these ports here, the first thing that we did is we moved all these ports into discarding state, and now at this moment we are sending our own proposals. Basically, what we are doing at this moment on these switches here, we are triggering their own synchronization process. So if these switches have downstream switches here, they are going to repeat the same process that we have started here. So what happened here is we had the proposal, we are sending the proposal, and the proposal goes out just like this. So once we send our own proposals, we are basically going to be expecting and waiting for the agreements to arrive. When we receive the agreement message on the port on which we have sent out the proposal on, we are immediately going to transition it into the forwarding state. So basically, what happens here in our example is when this switch here may have agreed with the agreement, at that moment, we are going to start forwarding here. So this port is no longer going to be blocking. This one is blocking or discarding, and this one is discarding. But this port here has transitioned to become a designated port in a forwarding state. So once that has happened there, we have moved our port into the forwarding state and the synchronization on this switch has been completed. Let's now see all this in action. To do that, I'm obviously going to use some equipment, and let me quickly show you what this equipment is going to be. So to start with, I'm going to configure two switches. I will be adding one more switch down the road, but I can start with just two switches. These are going to be my switch number one. I'm going to call it Cat1, and I'm going to have Cat2 here. They're going to be interconnected on Fastnet 24 port. And I'm going to configure these two switches to run rapid per VLAN spanning tree plus, and I'm going to configure Cat1 to be the root. And I'm going to make sure that Cat1 is the root by setting the lowest possible priority there. I'm going to configure priority 0 on this switch. Also, what I'm going to do here now, this is not necessary, but I really want to simplify things for me. I'm going to configure both of these ports here as access ports. I don't have to do that, I can leave them to be trunks, but what I really want is to see the behavior in just a single VLAN. Now, if I have multiple VLANs on the port, the same process will happen in multiple VLANs. I'm just going to be seeing more BPDUs than I actually need to examine the behavior that I'm after. And the behavior that I'm after is actually the behavior on this port and in general on Cat2 switch. I want to see what Cat2 does with its ports, how it transitions from one state to another, and I want to see my handshake and synchronization process in action. To do that, I'm going to be using the combination of two tools. I'm going to be using some debug commands on Cat2, and also what I'm going to be using is going to be my handy Wireshark, which is going to be connected to Fast Ethernet 03 port here on Cat2. And to start with, I'm just going to mirror the traffic from this port to my Wireshark station. So let's go ahead and configure this. Before I show you the configuration I promised, I'm going to show you something else, something that I have not yet talked about. What is going to happen if I configure one switch to operate in rapid mode and the other switch to operate in a non-rapid mode? Well, the answer to that question is very simple. The switch configured to operate in a rapid mode is going to fall back and operate in a traditional spanning tree mode. Luckily, this is very easy to test and prove. I'm simply going to leave cat2 in its default configuration and it's going to operate in a traditional spanning tree mode. I'm going to configure cat1 on the other hand to operate as I described I would. I'm going to make sure it's the root for VLAN 1 and I'm going to change it to rapid per VLAN spanning tree mode. Let's go ahead and see what's going to happen. Now keep in mind that there are some timers involved and I may need to move a little bit fast. So what I'm going to do on cat1, I'm going to change spanning tree mode, rapid PVST. I'm going to say spanning tree, VLAN 1, priority 0. So this is going to make sure that cat1 is operating in rapid mode and that for VLAN 1 it is going to become the root. Well, if cat2 is in default configuration, which it is. And I'm going to go to interface fastnet 24 and I'm going to say no shutdown. Very quickly here, I'm going to say show spanning tree and I'm going to do the same thing on cat2. Now, what I should be seeing here is on cat2, I see that port moved into the listening phase, but I can see that on cat1, because there is no listening phase in rapid spanning tree, this port is actually in a blocking state for the forward delay time. After that expires, it is actually going to move into the learning phase. In the learning phase, we are basically learning what are the MAC addresses on the other side. And this is the same thing that happened on cat2. Cat2 normally transitioned to learning phase, while, as I said, timers are involved, so I was a little bit too late. So there was a learning state involved on cat2 as well, but now we are already in forwarding state, which should be the same case on cat1. So now we can see that this is a designated forwarding port. But the important thing is that on cat1, on the side that was rapid, we had a transition from blocking state into the learning state and finally into the forwarding state. So we could not benefit in this case from our handshake and proposals and agreements because cat2 was unable to answer any of this stuff because it was running the traditional spanning tree. Now let's configure this properly. Let's configure both sides to run the rapid spanning tree. Basically, what we have to do is just change the configuration on our cat2. So I'm going to go to cat2 and I'm going to say spanning tree mode, rapid spanning tree. And I'm just going to reconfigure my ports to be access ports. So switch port mode access, they will be in VLAN 1 by default, but let's make sure that I do the same configuration on both sides. So spanning tree mode access here. Actually not spanning tree, but switch port mode access. Let's bounce the port. Actually, I'm just going to shut it down on both sides because I now want to focus on what is happening on cat2. As I said, what I want to do here is I want to observe the debug outputs on cat2 and I want to capture some traffic in my Wireshark connected to Fastnet 03 on cat2. So I need to configure the debugs and I need to configure my span session to make this happen. So I'm going to go to cat2 and the first thing I'm going to do is make sure that Fastnet 03 is up. Now this is the port facing my Wireshark. Then I'm going to configure my span session. I'm going to say monitor session 1 source interface Fastnet 24 and monitor session 1 destination interface Fastnet 03 encapsulation replicate because I want to preserve all the tags that might be going on there. And I'm going to go to interface Fastnet 24 and I'm going to again make sure it is shut down. Then I'm going to go to my Wireshark. Oops, wrong button. Let's go here. And I'm going to start the capture on the port facing my cat2. And here in the display filter, I just want to capture STP frames, which is basically an instruction to Wireshark to capture only the BPDUs. So going back to terminal, now I'm going to enable the debug. I'm going to run a very simple debug. I'm going to say debug spanning tree events. What I want to do here, or what I'm going to try to do, now keep in mind that this is timer sensitive. Timer sensitive in a sense that when the ports initially come up, both cat1 and cat2 are going to send their own BPDUs. What I want to try to do here is I want to try to catch cat2 sending the proposal as well as cat1 sending the proposal. Now, if I don't see that happening, I might need to shut the port down and do the no shut once or twice before I actually can catch it in that state. So wish me luck here. So the ports are now shut down. Let's see the state on cat1. Here I want to see administratively down, so I'm just going to bring the port up on cat1 because I want to do the no shut on cat2 side. So now what I'm seeing is that interface is down down, which is good. On cat2 I'm going to say no shutdown and let's see what happens. This is very good. Now I have this in the state that I wanted to have it in. The first thing that I am going to observe here is this message that says initializing port fast Ethernet 24. Now this simply means that the switch is preparing this port for spanning tree operations. The next two lines here are telling us that cat2 is now treating fast Ethernet 24 as a designated port, and we can see it was actually transmitted the proposal message. However, we know that cat1 is the root because we have configured it to be so. So when we receive the proposal from the other side, basically what we are going to do is we are going to update the roles and we are going to change this to become a root port. Now remember, in rapid spanning tree, root port transitions to forwarding state immediately. The next thing that we are going to do is we are going to generate the TC trap, which basically means we are going to generate the topology change notification for this port, and more importantly, we are going to transmit an agreement as the response to the proposal we received. And at this stage, the port has already changed state to up. So we can see here in the debug this proposal and agreement going on. Now, let's see the same thing in our Wireshark. So I'm going to first stop the capture here because I have captured enough packets, or frames I should say, and let's focus on what is going on here. Now this is going to be a little bit maybe confusing because of very similar addressing scheme that we have. Now we see that both switches 1 and 2 actually have the last octet as 9A, so we have to figure out which one is which here. Now remember, what was the first thing that we've seen? The first thing that we've seen was a proposal being transmitted. So we can say that this 17.5A9A, that this is actually cat2. And we can say that this switch that we are seeing with 0C5E9A, that this is our cat1. So let's see how this communication went. So if we take a look at the frame, we're going to see here that obviously we have some bytes on the wire, we have the Ethernet frame, the logical link control, and obviously we have the spanning tree BPDU. Where we are going to find information about proposals and agreements is going to be in this part that talks about BPDU flags. Proposals and agreements are not separate messages, they are not separate kind of frames, they are just simple flags in the normal configuration BPDU exchange between two switches. So here we can see that one of these flags means that we are sending a proposal, and if this bit is set to 1, this means that this is a proposal message. So this is the proposal here sent by our cat2. How do I know it's cat2? Well, I can see here, if I scroll this up just a little bit, I'm going to see here that the bridge identifier talks about the priority of 32,768. This is the default number, and cat2 had the default priority. So I can see here that cat2 is sending the proposal. Now let's see here what happened in this frame. Now this is the frame sent by cat1. How can I say? Because I can see here that the bridge identifier is 0, which means it's cat1 because I set the bridge priority to 0 on cat1. And here we also see that the proposal message has been sent. Now let's take a look at what cat2 did in response. Take a look. The proposal is now no, but what is set to 1 is the agreement. So Cat2 immediately agreed that this is how the topology should look. So we can see that this topology change, that this topology agreement, proposal sent and agreement sent, happened relatively quickly. Now, let me show you that in the terminal one more time. So what I'm going to do here now is I'm going to go to Cat1 and I'm going to shut the port down. Mind you, I have not turned on any debugs on Cat1. So what I'm going to do next is I'm going to turn off all the debugs on Cat2. And what I'm going to say is here, no shutdown. And I'm going to say, do show spanning tree. Basically, I can see here that the port is designated forwarding. And here on Cat2, I can see that the port is root forwarding. How long time did this take? It happened almost immediately. Now we know it wasn't immediately because of this proposal agreement negotiation, but it happened much, much faster than it would have happened in the traditional spanning tree, which we have seen about 5 minutes ago. Remember how long time it took? We had to transition from the listening phase into the learning phase and the forwarding phase on a non-rapid side, and in a rapid side it was the blocking, discarding phase, then the learning phase, and only then we could move into forwarding, which was controlled by the forward delay timers. In this case, there are no timers involved because we are going to send our agreement after we have performed the synchronization process. But keep in mind that in our case here, the synchronization process was very, very simple on Cat2. There were no other ports that were up. What happens when we add the third switch? I'm going to add Cat3 to the mix here by connecting it directly to Cat2. And this is going to be connected on Fast Ethernet 020 on both sides. I'm not going to change any configuration that pertains to root election, so our Cat1 is going to remain the root here. But what I am going to change here is the configuration of my span. Now I'm going to modify it to actually get the traffic from this port here and send it to Wireshark, because I want to see these proposals and agreements as they are communicated between Cat2 and Cat3. I'm also going to keep on running my debugs here on Cat2, and I'm going to enable similar debugs on Cat3. So let's go ahead and configure this stuff. So I have Cat3 here, and what I'm going to do is I'm going to change the spanning tree mode to rapid spanning tree. I'm going to change spanning tree VLAN 1 priority 61440. I'm going to make sure that it's not going to become the root, and interface FastNet 020, and I'm going to say switch port mode access, and I'm going to say no shutdown here. On Cat2, I'm just going to prepare FastNet 020. Actually, it was already up, so let me just shut it down here, switch port mode access. And I have shut it down, and I'm going to say no monitor session 1. I have removed the session 1, and I'm going to say monitor session 1 source interface FastNet 20. And I'm going to say monitor session 1 destination interface FastNet 03 encapsulation replicate. So I'm going to create my span session just to make sure that FastNet 03 is still up. I'm going to make no shutdown there. And I'm going to go to interface FastNet 20, and I'm going to prepare for no shutdown there. On Cat3, I'm going to say debug spanning tree events, and I'm going to do the same thing on Cat2. Do debug spanning tree events. So now I'm ready to do no shutdown here. After I configure my capture here, let me start it from scratch. So I'm capturing traffic again from Cat2. And I'm going to say no shutdown. Let's see what happens here. So now FastNet 20 is going to transition, it's going to become a designated port. We are transmitting a proposal, we have received an agreement, and that's pretty much it. Now, from Cat3's perspective, remember, we are going to transmit the proposal, we are going to update the roles, and we are going to transition FastNet 20 to become the new root port. And here in my captures, I should be seeing pretty much the same thing. I can see, let me stop the captures to prevent this from scrolling. What I should be seeing here is that the proposal was sent. We can see that the proposal was sent, and then we can see that the proposal was received. Here we see that the proposal message has been received, and here we are finally sending our own agreement. All the subsequent BPDU messages are not going to have proposal or agreement bits set here. So this is how it works when we add the third switch into the mix. But I don't really want to leave it here. I want to show you one more thing. Now, at the beginning of this talk, I mentioned that part of the synchronization process is that the ports are going to be moved into the disabled state. Then all those things are going to happen, and remember what those things were. So we are going to send the move the ports to discarding state, and we are going to send the proposal message on downstream switches. But here, if I take a look at the debug on my Cat2, nowhere does it actually say that any ports were moved to disabled state. Now, the reason for that is that that happens really, really quickly, really, really fast. And I have been actually, in the meantime, before I recorded the previous tiny little segment of this video, and now, which is about, I would say 25 minutes later, I have been trying to actually catch it with the show commands, and I realized that there is no way I'm going to be that quick. And let me show you why there was no way to be that quick. So what I'm going to do now is I'm going to shut the Fast Ethernet 24 down. So on Cat2, this is the port facing our Cat1. So I'm going to bring this port down. I'm going to get some debug output here from my current debug, and I'm going to say undebug all because I want to run a different debug command. So this is going to be debug spanning tree switch, and what I want to see here are the port state changes. So I'm going to run a different debug message here, and let me go back here, interface fastnet 24, and I'm going to say no shutdown. So let's see what happens now. So there we go. Now, take a look at this. I have moved Fast Ethernet 24 from one state to another. So let's ignore what was happening with Fast Ethernet 24. Let's focus on what was happening with Fast Ethernet 20. Now, you see that here, at this point in time, there was a blocking request for one VLAN. One VLAN because we are dealing only with VLAN 1. Now, this happened here at whatever time it was, at 0.803 of a second. Now take a look at here. This is happening less than 20 milliseconds later. So it's happening 17 milliseconds later. What we are seeing here is that the port changes state from blocking to forwarding, because we have sent our agreement, the stuff has happened on the other side, and we have received, sorry, we have sent our, we have sent out the proposal to the other side. The other side, our Cat3 performed what it needed to do and sent back the agreement. It happened so fast that we cannot actually possibly catch it in this short period of time here. We can see here that at the same time we were actually receiving this blocking request, we transitioned Fast Ethernet 24 to forwarding. So this has happened, this moving into the discarding state and transitioning back to forwarding, but it was so quick, or I should say so rapid, that there was basically no impact on the forwarding traffic. Last but not least, let's examine what happens when there is a topology change in a rapid PVST network. First of all, the topology change is a little bit redefined from the traditional spanning tree. In the rapid spanning tree, the topology change event is basically a non-edge port transitioning to forwarding state. So if the port goes down, we don't really care about it. We only care if the port starts forwarding, and it's a non-edge port. When that happens, two separate things happen. Now, I'm going to talk about the last thing first. Just like in the traditional spanning tree, we are going to send out the TCNP PDUs, and they're going to propagate the same way they propagate in the traditional spanning tree. This is used for backwards compatibility. in a case that we have switches in our network that don't understand the rapid spanning tree process. The other thing that happens is much more interesting. The BPDUs, just like the ordinary configuration BPDUs, are set with the TC flag set to 1. Now, this is sent out of every non-edge port. When a switch receives this BPDU, what it's going to do, it's going to flush its CAM address table on all designated ports, on all non-edge designated ports, and it's going to forward this BPDU on, similarly to the way synchronization process happens. So we can think of an ever-expanding wave of these BPDUs with the TC bit set to 1. Also, this is going to happen from the originating point, from the switch where the topology change actually happened, for the duration of 2 hello timers. So by default, we are going to be observing this 2 times, so 2 hellos are going to be sent, 2 BPDUs are going to be sent this way, because this is the default timer of 2 seconds. So this is very, very simple. You can see that it is slightly redefined, but if we understand the synchronization process, the proposals and agreements, we are going to understand how the topology change is propagated through the rapid network.